People are going to see my amazing notes. Apparently quite a lot. Come on, you piece of crap. I know. Can't be swearing on air. That's just so.
I put it from another one now. Push it over a bit that side.
We are live. So.
Yeah, well, I told you not to. All right.
Good.
Cool.
Okay, we can start.
Okay. So, hello. My name is Matthew Franklin, and I'm here to talk to you about text search. So, I've created a book website. It's got every single book that's ever been made. I'll close the door now, if you want to enjoy. Yeah, it's got every single book that's ever been made. And here, for those, is the website that you can use to search for your books. All you have to do is enter the ISBN and you'll find your book. No problem. Now you think that that's crazy, right? Because we got like search engines like Google. But this really exists. Is it going to show up? Yeah. So there are websites that think that this is a good way to go about searching for documents. What you're more used to is probably something a lot like this, which is where you basically enter what you want to find and then it shows up. You know? And this is fundamentally what text search is. So if you think about it, Google has an index over the whole internet, and you enter a phrase or a term, and then it finds all documents that match that. And it's not just enough to find them, it also ranks them so that the most relevant one, Moby Dick, turns up first. So, look. I'm going to make this full screen in 1 minute, but it doesn't matter. Basically, this presentation is going to go over the fundamental approach that text search takes in order to determine what documents match and how to rank them, and then how you can incorporate that into your site or application, and then how you can make sure that everything stays up to date. So, the first thing that you need to concentrate on is making sure that everything is normal. What I mean by this is things like the case of your words. So if you think about it, if you did an exact match against two words and they differed only in case, then really they represent the same concept, but they wouldn't match because an uppercase letter differs from a lowercase letter. The very first thing you need to do is to have a consistent case. The next thing is that, you know, Unicode is a wonderful thing, but it makes things a lot more complicated. So here we've got several different letters that can have multiple representations in different forms of Unicode. So there are at least 4 different forms of Unicode, and some of the letter combinations can be rearranged in different orders, so you can end up with quite a large number of representations of a single letter. So what you need to do is you need to pick a consistent form and then normalize all your text so that it belongs in that form. And then you get on to this, which is the idea that your words that you're searching for aren't really the exact things you're looking for. Instead, what you're thinking about is like the underlying concept. And so the words that you've entered may differ because they may be plural or they may be singular. Or they may relate to things in the past or the future or active things that you're doing. And so you need to take all of those words and reduce them to their root form. Okay? Once you've prepared all of this, you then get on to matching. So how do you determine which documents match your original query? So the very first thing that is important to realize is that the choice of algorithm strongly dictates the index that you can use and the way in which it matches specific documents. So it happens that Postgres supports 2 kinds of indexes, one of which is like a Bloom filter. So here we can see that this Bloom filter contains 2 different words. Now, Bloom filter takes an entry, it hashes it, and then it sets that appropriate index in a large blob of memory. If you then want to determine if the hash contains the word that you're looking for, what you do is you hash the word, and then you look at the same index. If the index is set, then you contain that word. Now, if you can take all of the words in the whole document, and hash them in this way, then you can produce like a signature of the document that you can then match against. Now, this has obviously got some problems because if you have a hash of a word, then it's like reduced in some way. And this reduction can lead to collisions. So two different words can result in the same hash. And this means that when you've checked things with the Bloom filter, you may have some false positives. Those false positives need to be filtered out by loading the entire document and then actually checking that it contains the words that you expect. So this is very fast initially to create the blob of memory, but because it needs to load everything in order to check it a second time, it ends up being slower in practice. The most popular form of index, which is used by over 80% of text search, is the inverted index. And here, what you do is you take every single word that is in the document or in all of your documents, and you index them, and then you list the words which list the documents which contain that word. Okay, so in this example, you can see that the word one appears in many of the records indicated by the blue arrows. So, 4 of them. And these form sets. In order to determine the set of documents that contain all of the words in your query, you just find the intersection of all of the separate sets. Okay? And then we get on to stop words. Now, stop words are extremely frequent. They turn up in almost every document. And they have very little value because they're so frequent. And you can actually speed up your index quite a lot if you exclude them. Now, the problem here is that excluding them, while it speeds up your index, it makes certain forms of search impossible. So searching for to be or not to be doesn't work if you've excluded stop words. Now, in modern text search engines, they actually have techniques which try and minimize the impact that stop words have on speed, but still allow them to exist in your query and to influence the output that it produces. So we've briefly covered how text search works. But it still doesn't cover the fact that when you search Google, you usually find about 1 million documents, and you couldn't go through all of that by hand. So it's very important that not only do you find these documents, you're able to rank them. And so we get on to ranking. Now, ranking is the process by which you put the most relevant document at the top of the list. And Google is very good at this, for example. Most people never click on page 2. And the first thing that you can do to try and get your most relevant document is to look at the number of times that the terms in your query appear in the document. So the more it appears, the more likely it is to be relevant to your search. Now there should be an obvious flaw with this, and that is that if you have a very long document, then you're going to have a lot of matches, and that's just because it contains a lot of words. So while considering the term frequency, you should also consider the length of the field that contains these terms. So if it's a very long field, then you reduce the impact that has on the overall ranking score. And this then leads to a match in the title, which is typically short, being far more valuable than a match in the body of a document. And then we get on to a more holistic approach where you consider all documents. So if you have a word in your query which appears only in a few documents, then that is likely more relevant to your query than one that appears in almost every document. Now, if you look at the way that you rank this, it works to counteract stop words, because stop words appear in almost every document. And so if you can implement this correctly, then you'll naturally reduce their impact on the ranking. Now, the way that this is normally done is called term frequency inverse document frequency, which is much like it sounds. You take the number of times the term appears, and you divide that by the number of documents in which it appears. So now that you're able to search for documents and rank them, we can then talk about how you can incorporate this into your website, application, or whatever it is that you're using. So here we've got two possible options. This is the Postgres user group. It would be remiss of me not to mention Postgres. And we should also mention Elasticsearch, which is built on top of Lucene, a reputable search engine for text, which has existed for almost 20 years. It's also the thing that underlies Solar. Postgres is very flexible. It's able to do far more than text search. And it's got many, many different index types, for example. And this flexibility allows it to be highly customized to a specific use case. For example, Postgres supports both the Bloom and the inverted index types. Now, Elasticsearch is far more specialized than that. What it provides is finely tuned over many years of development, but it only provides the inverted index. And whilst you can make your queries more specific by enhancing the impact of certain fields and things like that, it's relatively limited when you compare it to Postgres. Now, Elasticsearch is specialized even further in that it's not very good at the things that Postgres excels at. It has poor relationships between documents. Okay.
Yeah, it's quite quickly. So.
Okay. And it has poor support for transactions. So, it's unsurprising that since Elasticsearch specializes so heavily in this area, that it would be faster than Postgres. Now, at this point, I should mention that this presentation is a repo, and it actually has quite a lot of tools that will allow you to determine this for yourself. And in my tests, I found that Elasticsearch was 10 to 100 times faster than Postgres. So the difference is quite dramatic. Now, I didn't put these numbers here because it wasn't particularly scientific, the testing that I performed. And so if you wish to tune finally both boxes, you may find that you can produce some different results. It's just difficult to believe that you could improve Postgres by 100 times. So it's good to remember that Postgres is also specialized. And what it specializes in is relationships between different tables and complex transactions. And these are things that Elasticsearch doesn't do so well at. So, bearing that in mind, why can't we have both? And yeah, maybe I should have made it full screen. She's saying, why don't we have both? You haven't seen this GIF before. So now we're going to get on to the most important thing, which is the foreign data wrapper. This allows Postgres to represent a remote service as a table. When you read from the table, you're really querying the remote service. When you write to it, you're updating the remote service. Everything that the foreign data wrapper is doing is implemented using code. So you could do arbitrary computations based on queries. So it should. So what we're doing is basically taking Elasticsearch, which has a REST API, and using it as a table. Now, like I said, Elasticsearch is basically a service and it's also a database. So it's unsurprising that it should be well represented as a table within Postgres, because that's basically what it is when you're using it normally. And so what you can do is you can query it when you query the table. It will return JSON. The foreign data wrapper can then unpack that and then convert that into rows that you can use in Postgres. And there can be joins and so on if you make sure that the data in Elasticsearch matches up with the data that you have in Postgres. So this sounds great. It exists. You can go and use it right now if you want. And I'm just going to go quickly over how you can implement a foreign data wrapper in this. And if you want to take notes, then I'm quite happy to talk to you about this afterwards. I'll just give a moment, because someone's taking a minute. Cool. Yeah. So I'd scroll a little bit, but essentially this is the set of commands that you need to run in order to set up the server. What this does is it just installs a few packages, and then pip installs Elasticsearch, which is the Python library required to make requests to Elasticsearch, surprisingly enough, and then clone the repo that I just mentioned, and then you can just set it up. Once you've done that, then it becomes available within Postgres. The thing you need to do is you need to create the extension and then load the specific foreign data wrapper implementation that Multicorn provides. So at this point, I should point out that Multicorn is a Python library that allows you to implement foreign data wrappers. And that's why we're creating the extension for that. And then we're providing options for it, which relate to Elasticsearch. So once we've done that, we can then create the table. Now this is one where I really should scroll. So, where's the mouse? Here we go. What this does is it's just setting up a table that matches one that happens to exist in Postgres. So I've set up ID, title, body, and query. Now 2 out of those are special columns. And that's because I've said that the row ID column is ID. And this will then correspond to what Elasticsearch believes the document ID to be. Okay? The second one is that we need to be able to query Elasticsearch, otherwise it's not much good, because if it contains like 17 million documents, you don't want to receive that every time you make a single query. So we need a way to pass this query in. And so we've got this virtual column, which doesn't really exist in Elasticsearch, but it's a way to refine the documents that we get back. And so that's the query column. And so I'm not going to force you to watch me type this out, but this is basically me running a search against the whole of Wikipedia. And you can see that the first query is against a field, which is the body. Yeah, and it's for Asia. And the second one is one that would be filtered out using the default settings of Postgres, which is a search consisting entirely of stop words. So the is a band from the 70s, if you're not familiar. Okay, and you can see that, you know, relatively speaking, it's pretty fast. So you've got your data in Elasticsearch and you've got it in Postgres, but how do you keep them the same? That's a big problem because ultimately, you know, if you're using this as an index over the data in Postgres and it doesn't agree, then it's going to return junk, isn't it? Like it might return documents that have long since been deleted or updated, or it might miss new documents that it should have matched. So, as I mentioned earlier, the foreign data wrapper is able to write. So from this, it may seem obvious that you should use triggers. You know, I had a chat with someone just about an hour ago, and they said triggers. Yeah, and it's a great idea. Like if you've got a small set of data, you could totally use triggers, keep it up to date. And there are a few problems though. So the first part is the foreign table must be separate from the original table, and that's why you'd have to use a trigger in the first place. And that's because if you think about it, if you tried to mix foreign columns with local columns, what would happen if the remote service disagreed with you about the existence of a column? Yeah, so the table would become inconsistent because some rows would have data and some wouldn't. So you need to use a trigger from one table that exists locally, and then you can fire off an update against your remote table. So the problem with this, even further than that, is that transactions will fail. And like I mentioned, Elasticsearch has poor support for transactions. So imagine you had a transaction that was several different statements. One of them happened to update your table. That then fired a trigger. The trigger then wrote to Elasticsearch. The transaction failed. You'd then have to, in some way, roll back Elasticsearch. That would be quite tricky to do because you basically need to record every single document that you're about to update. and then be able to write them again. And that would be how you'd achieve rollback. And it sounds pretty bad when I'm saying it now. You know, just wait until it gets into production. So what you really need is a way to be able to crank out those duplicates, you know, be able to take a new box and make it into a new Elasticsearch, which is up to date, or even to take a new box and make it into a new Postgres, which is up to date. So if you have it like that, then if it breaks, you can just replace it, and it's not a problem. So now this sounds quite a lot like ETL. If you think about it, a lot of the time when you're doing analytics over a large data set, there might be a cron job which fires off overnight and completely recreates the database based on some source database. It can extract all of the data and then load and transform it into the correct form. Now, obviously, ETL may be fired off as a batch job like this, but the concept itself doesn't rely on being run like that. It could be run on a single record, for example, or it could be run in real time. So at this point, we're then talking about like how you manage the flow of data in your application. Now, as programmers, we love to try and clean up our code. Refactoring is a really great waste of time, and we really want to avoid spaghetti code, where you have an application where all of the responsibilities are tangled and everything's calling everything else, and there's no clear division of responsibilities. If you think about it, as we move towards microservices, this is an attempt to like limit the damage that each individual part does. And it also clarifies the data flow between them. If you were to create yet another strand of spaghetti between your Postgres database and your Elasticsearch database, you would be making this web of interconnected flows more complex. Perhaps what you need is a more holistic approach. And that would be the ordered log approach. So the essential idea is that you have a commit log. So a commit log can be implemented using many different technologies, but it's basically a service whose job it is to provide an ordered list of messages. Now these messages can represent the changes that you are applying to your system as a whole. You then replay those messages into the individual databases or your cache or your stream processing system in order to bring that system up to date to the latest state. Now, this allows you to decouple Elasticsearch from Postgres and keep the two in sync separately, independent of each other. It should also be obvious that if you can have this kind of system, then you could easily start up a new instance, replay the messages in a log, and end up with a complete and working and current system. And you could then incorporate that into your larger, application stack. So the core thing that I'm saying here is that if you've got multiple different machines that do different things and you apply the same actions to them, they should reach the same state. So when you're performing your search in Postgres and it happens to ask Elasticsearch, it's going to get back data which is consistent with its own worldview. Okay, so obviously this depends on being up to date with the log. Now it may be that for some reason one of them is running a little bit slower than the other. Now this ordered log has offsets or timestamps available to you, and if it really matters that you serve up-to-date information, then you can ask that your request only be served at a specific point or later. And this would allow you to handle a situation where, for example, someone lists a new product on your site and you don't want to return the response until that product is available in the database. Otherwise, it may appear that their upload has failed. So when you view things like this, your entire system consists of data and indexes over that data. And if you use the ordered log in order to keep everything in sync, then you can apply those changes consistently to every single system that forms that entire application. Now, you know, this is really great, like I mentioned, for terms of replication and restoration. So if you have an instance which, you know, appears to be working okay, but maybe it's just a little bit funny, then you can stop it and you can just fire up an instance that's alongside it, replicate it until it becomes up to date, and then you can easily make sure that you've got a new thing that can replace the old thing. And if you've got enough data to worry about this kind of system, so if failure is going to happen, it's more a case of when. I really should have a faster laptop. But yeah, fundamentally, the log is the way in which you populate these databases to begin with. You are going to take snapshots or backups because if you're running this system over a long time, this log could become very large and you wouldn't want to keep it forever. Even if you did keep it forever, it could take so long to restore that, you know, you've gone out of business by the time the actual database is ready to be used. So you need some sort of intermediate point. So maybe take a weekly backup and then have a log that lasts for at least a week. And you should be able to replay that set of changes relatively quickly. One main benefit of using the log in order to bring new systems up to date is that you know it works. It was the way in which you were using the site before it broke. So it must be pretty good. And you don't have to worry about having a backup system which is barely tested. And then when calamity strikes, it turns out that, hey, oh, you forgot to apply some schema change. And now you suddenly can't use anything, you know? And so that's the end. And I kind of rushed through all of that, but basically that goes over how text search works, how you can use it in Postgres or Elasticsearch, how you can keep those systems in sync. Now, I'm happy to take any kind of questions that you have. And I'd remind you that this website is on GitHub, and all of the supporting materials are present in there, such as the performance tests which I ran, which I remind you are far from scientific. Yeah.
I have a question about the you shown us the a diagram about the application log.
Oh yeah, yeah.
Are you aware about the bottled water?
Yes, exactly. So
Because I was just looking to the similar thing.
exactly. So if you think about it, like the things that read from your log don't have to be just readers, they can also be writers. You can have many different topics. So, for example, you could have your website where people click around and they like view pages or like things or whatever. And then that data flows into an initial database that might be your source of truth. That could then write again to the log using something like bottled water.
In this case, is the application writes into Postgres, and then the logical decoding is used for feeding Kafka.
Yeah.
And then Kafka sends the changes to Elasticsearch.
Yeah, exactly. Obviously, you want to structure everything such that you're able to restore the log. So with that idea of Postgres being the source of truth at the beginning, all you need to do is back that up, and then you'd be able to restore everything that occurred on the log. And this is especially true for PG bottled water, because it's able to take a database and manually rewrite it to the stream, to the log, sorry.
Interesting. Are you planning to release this thing Pi?
I am, yes, but I was a little bit busy to do that right now. But yeah, I've obviously been using it for this, and I've been knocking off a few rough edges. But yeah, I hope to release it on PyPy perhaps later this week. And that should, you know, improve the installation process slightly. So, any other questions?
I kind of have a tangential question.
Yeah.
Seeing as I'm an expert, I mean, I thought I'd ask anyway. Do you think there's much of a Google Scholar and Google? Are they fundamentally the same? They just use different data sets, or is there something more underneath that's driving the quality of the search?
So you mean Google Scholar valued book search?
Yeah, academic search engine.
So obviously Google's so large and so well provisioned with engineers that they're able to create fundamentally differing text search should it suit their needs. So I would suggest that someone probably had a lot of time on their hands and they probably rewrote it. Fundamentally though, the same principles apply. You know, find the book that is most relevant to your search. And your search is by intent, not by the specific string of words that you might use. And so even if they did rewrite it from scratch, it would probably end up much the same. Yeah. Anything else?
And I think you should make the replication from log, etc., into its own tool.
Oh, probably, yeah. Just sort of jammed everything in.
Yes, because that was enough on its own, I think. You know, but yeah, that's all very.
Yeah, so if you are interested in that, there's a very good blog post from LinkedIn. So LinkedIn created Kafka, which was one of the original log systems. And they've got a very, very good blog post about how you can use this. It's basically the data backbone for your organization. Yeah.
Is Kafka supporting the retention, right?
That's correct. So Kafka has a few different modes. It's able to retain messages by the duration, so maybe a week or 2 weeks or a month. Or you can do it by disk space, or you can do it by a combination of both. And the second form is more interesting though. If you have a set of messages that you're able to always store, you know, they don't take up too much space, then you can have what's called a compacted log. Now, a compacted log behaves normally like a regular log, except that the retention policy is infinite. Every message on it has a key. Whenever a new message arrives with the same key as an old message, the old message is discarded. And you can think about this in the same way that a table works. So you can add new rows and you can delete rows, but if you update a row, then the original value is lost. And if you're able to support it, then you could store your entire log in compacted form. The chances are, though, that if you were able to do that, then you probably wouldn't have these problems. Because if your data set is small enough to fit in a compacted log, you could probably just use Postgres text search and it would be fast enough.
Last question for me.
Yeah.
Is a DBA question. Difference in size between Postgres and Elasticsearch?
Okay, so Elasticsearch inflated the original data, which I admit was in XML, so it was pretty big to begin with. It went from about 64 gigabytes to about 80 gigabytes. Postgres, it was about 30 gigabytes. So Postgres stored it in a much more efficient way. Very good.
Postgres, which format are you storing? Just text?
Yeah, just text. So it would have been toasted and compressed.
Okay, so it's the toast that you mean.
Yeah. Because ultimately, like I didn't clean up the input data at all, so it had a lot of like links and wiki markdown and stuff like that. But fundamentally, it's still just text, and text compresses very well. So when the document became too big to store in line, it was written to disk in compacted form. Anything else? Oh, okay, well, thank you very much.